Alright, we're going to go ahead and get started with Unit 2, known as Atoms, Elements, and Compounds. And within this unit, we're going to look at some basic ideas of chemistry. Many of these ideas you're probably already familiar with, but nevertheless, it will be a great refresher to you. And there might be a few things that are also new. Alright, to start out with Unit 2, we're going to look at the basics of what matter is. And so, Lecture 1, which is known What's a Matter, is going to cover those basics of matter and elements and compounds. Alright, so let's look at the essential question for Lecture 1. What are the building blocks of matter? So by the end of this lecture, you should be able to answer this question, and you should be able to be prepared to answer it on the quiz that we'll have in class over this unit and lecture. Okay, so let's start out with a simple question. What is matter in the first place? Many of you probably already know the answer to this, but let's make sure. So matter is anything that has mass and takes up space. Another way of looking at space would be the unit or the measurement of volume. So matter has either mass, well, has both mass and volume. And if an object or something that does not have mass or volume would not be considered matter. Can you think of anything that might not be matter that has mass and volume? One of the things that comes up a lot is energy. In chemistry, we deal with energy quite a bit, but energy does not have mass and volume. So therefore, energy is not matter. And fact is, in chemistry, the two things that we spend our time studying is matter and energy, and how matter and energy interact and relate to each other. And you'll see this throughout the course of the year. Alright, so there's our class definition of matter. Alright, elements. What exactly are the elements? Well, first of all matter is made up of submicroscopic, which are very small particles called the elements. Okay, so what do we mean by submicroscopic or very small particles? Well, what we're referring to is particles that cannot be seen with the visible eye, nor can be seen with a regular light microscope. In fact is, we have to have very, very special microscopes to even begin to glimpse at the surface of elements. So we call them submicroscopic. Elements are considered really more or less the building blocks of all matter. Which essentially means that all matter in the universe is composed of or made up of elements. And an element is a unique form of matter that can exist on its own or in a combination with other elements. And this is really important. Elements cannot be broken apart into two different substances by chemical reactions. You really need to have that little statement down packed. Okay? Again, you can't break elements down into other substances through chemical reactions. You can break elements down through what is known as nuclear reactions, and we will discuss nuclear reactions at another time. Well, right now there is about 118 known elements in the universe, and all the matter in the universe is made up of a combination of these 118 elements. Alright, so here we have an example of a gold bar, and this is what gold would look like to us on a large scale that we would see with our naked eye. However, what cannot be seen is the elements that make up this gold bar. And those elements that are submicroscopic, that are very, very small, are composed of the element known as gold itself. So we can consider that we've made a model particles of gold or elements. Alright. Now, because we can't see gold with the element gold with our naked eye, or even with a light microscope, a lot of times we have to make models to visualize what gold atoms or other elements might look like at the submicroscopic level. Alright, now each element has a name, like silver or potassium or Einsteinium, and it has a chemical symbol that represents that particular element. The symbols for elements consist of uppercase letters, which are sometimes followed by a lowercase letter. Note that each element symbol always starts with a capital letter, and that's important. Make sure you always start an element with a capital letter for its symbol. And there's some examples. Silver is Ag, Einsteinium is Es, and potassium is K. And notice that the first letter in each one of those symbols is capitalized. Alright, so just a minute ago when we were looking at gold elements, we were talking about the fact that we cannot see the elements of gold with our eyes. In fact again, we have to use very, very special microscopes to even begin to glimpse the surface of elements. So most of the time we build models to represent what elements might look like or how they interact or behave at the submicroscopic level. And so in this class we're going to make models to represent elements. We're going to make models to show how elements interact with each other to form compounds, or how elements interact to change what the look of matter is, or the properties and characteristics of matter that are useful to us. And so on the tests and quizzes and even homework assignments, you will be asked to draw models, make models that will represent matter in certain aspects. Okay? So models models are representations of what we believe matter is like and how it behaves based on observations and experimental data. And that little statement there that I underlined, I would highlight that in your notes. And that's a very important statement to think about what models really are. And just remember that they are representations of what we believe matter is like and how it behaves. Therefore, a lot of times we will refer to a model as a theory. And so make note that models are just theories on how we believe elements or other matter behaves. Models can change. They can be modified based on new experimental data. That's something else to make note of. Alright, here are some models. Here's some models that we're going to look at. This is a model of aluminum. Al is a symbol for elemental aluminum. And aluminum atoms are packed together to form this particular structure that you see here. And that is a model of elemental aluminum. And you'll see here, this is what we would view aluminum to be with our natural eyes. But again, we can't see the atoms of aluminum, so therefore we draw or make a model of what we believe it looks like. In the beaker over here, we have bromine. Bromine, from what we understand, is consistent of two bromine atoms that make up elemental bromine, and we model that by showing two circles that each one represents one bromine atom that combine together to form elemental bromine, or Br2. Elemental bromine is more or less a liquid at room temperature, and it has this yellowish orange look to it, and it easily becomes a gas at room temperature, as you can see in this beaker. So again, we can visualize and see elements with our eyes as far as what they would look like on a big scale, but as far as what an actual element looks like, we cannot see with our eyes, so we make models and draw models of them. Alright, so now what we're going to do is we're going to look at compounds really quickly. A compound is made up of two or more elements in fixed ratios. And they cannot be broken down into can be broken down into simpler substances or elements. So in other words, a compound is composed of two or more elements that are fixed together, and they come in a specific ratio. And we'll explain more what that ratio means in a minute, but it is really important that you understand that compounds are found in fixed ratios in the number of elements that are involved in that compound. And they can be broken down into elements themselves. Okay, a compound is represented by what we call a chemical formula. For example, copper oxide is a chemical formula. It tells us that copper oxide is made up of one copper element and one oxygen element. And therefore, it also tells us not only the elements that are involved in the chemical, but it also tells us, or the compound, but it also tells us the ratio, or the fixed ratio. And so in copper oxide, there's always going to be 1 copper for 1 oxygen. And so a chemical formula is just a way to represent a compound, showing us the elements that are in that compound plus the fixed ratio between the elements. So here in C, a chemical formula is a set of symbols a chemist uses to represent a compound. Carbon dioxide is a compound. It has a chemical formula of CO2. So C, which represents carbon, O, which represents oxygen, and the 2 tells us that it has 2 oxygens for every 1 carbon. And so that's a fixed ratio, or we'd say it's a 2-to-1 ratio, 2 oxygens for every 1 carbon. And that is true for every carbon dioxide compound. It always has a 2-to-1 ratio. Again, 2 elements of carbon, or 2 elements of oxygen to 1 element of carbon. Okay, so let's look at this a little bit closer. We have oxygen, and oxygen is made up of 2 elements of oxygen. So the chemical formula for oxygen would be O2. Water is made up of 2 elements of hydrogen and 1 element of oxygen, so it has a formula of H2O. And that means that in water, it has a fixed ratio of 2-to-1, 2 hydrogens for every 1 oxygen. And that exists all the time, no matter where you're at in the world or even the universe. Water has a 2-to-1 ratio, 2 hydrogens to 1 oxygen. Again, we talked about carbon dioxide being CO2, and it has a fixed ratio of 1 carbon to 2 oxygens, always. Now, ethanol has a formula of C2, 2 carbons, and it has, if you count, 1, 2, 3, 4, 5 hydrogens and 1 oxygen. So ethanol has the formula C2H5O, or a ratio of 2 carbons, 5 hydrogens, and 1 oxygen. And that ratio never changes. Alright, so ethylene glycol, which is more or less antifreeze that you put in your car, also has the formula of C2. It has 1, 2, 3, 4, 5 carbons, or hydrogen, sorry, and it has 2 oxygens now. So ethylene glycol is a little different than ethanol in the fact that there's a difference in the ratio between carbon, hydrogen, and oxygen. Okay, aspirin. Aspirin, if you count up the number of carbons, the ones in black, it's 1, 2, 3, 4, 5, 6, 7, 9. So there's C9 for 9 carbons. How many hydrogens? Let's count them. 1, 2, 3, 4, 5, 6, 7. So H7. And number of oxygens in red is 1, 2, 3, 4. 4 oxygens in red. So I would write the chemical formula for aspirin as C9H7O4. And it has a ratio of 9 carbons to 7 hydrogens to 4 oxygens. And aspirin will always maintain that fixed ratio. Okay, so the bottom line is that what I want you to understand is that a chemical formula is a way to represent compounds. A compound is composed of 2 or more elements that are found in a fixed ratio, and that ratio for that compound cannot change. Alright, so that pretty much sums up the first lecture. Go back and re-look at this if you need to. Make sure you study your notes and be prepared for the quiz that we will have in class. Alright.